Welcome back to the show that tells you you are a quantum computer with free will implemented in the brain by some yet-to-be-discovered mechanism. My name is Justin Riddle, and this is episode 24 of the Quantum Consciousness series. In today's episode, we'll be discussing why neuroscience is in need of a quantum revolution. By the end of today's episode, we'll ask the question, what does a biologically plausible quantum computer look like? This episode is available on YouTube, and an audio-only version is available on Spotify and Apple Podcasts. If you like what you hear today, then please like this video, subscribe to this channel, share this video with a friend, or for the audio listener, write a review.
Join me deep inside the mystery of numbers. Come and huff a metaphysical loo. See how concepts become objects and then become qualia. Join us for an episode of Quantum Consciousness.
Hey there, today I will be sharing with you a presentation that I'm giving at the Science of Consciousness conference in Tucson, Arizona on April 18th. So I've prepared this lecture, and this is basically a practice run through that I thought I would share with the YouTube channel. And so here we go. All right, so the title of this talk is Why Neuroscience Needs a Quantum Revolution. Some backstory on me. I am Justin Riddle. I got a PhD in psychology from the University of California, Berkeley, and I'm currently conducting a postdoc in the Department of Psychiatry at the University of North Carolina at Chapel Hill. And my research really began by studying the neural mechanisms, particularly neural oscillations, and how they play a role in various aspects of cognitive control, including memory, attention, and rule acquisition. And then going into my postdoc, I wanted to apply these ideas from neural oscillations to the domain of psychiatric illness. However, today's talk is integrating a lot of this work, but expanding it in a peculiar direction. And that is because at UC Berkeley, when I was a graduate student, I taught a course on quantum consciousness, and I voraciously consumed a lot of the literature and pop science related to quantum physics and how it might be applied to the study of consciousness. And I started a YouTube series where I go through these various theories of quantum consciousness. And so the idea of today's talk is really to just give an introduction to what quantum mechanics buys you, how it goes beyond classical theories of consciousness, and then what it will look like to genuinely move the domain of neuroscience towards incorporating more of these ideas from quantum mechanics. And I would argue that we are in need of a revolution and an update to our cognitive neuroscience approaches. So the topic for today, or the outline for today's talk, is the late adoption in neuroscience. And so I'll make the pitch to you that neuroscience tends to be more slow to pick up on the trends in physics and in computer technology. And so, just looking ahead, it seems like an inevitability that we would update the field given modern physics and given modern pushes from lower level biology. But for some reason, the domain of neuroscience, studying the whole brain, appears to just lag behind slightly. So part of this talk is really to imagine what that will look like in the hopefully near future. The second point of this talk will be talking about different mysteries of consciousness and how the quantum mechanics framework really sheds some light and provides some new ideas, some new ways of looking at these fundamental mysteries, which previously may have been written off as fanciful or beyond the scope of science. And in order to, provide a roadmap for the revolution in cognitive neuroscience, I'll tell you what I think are sort of the roadblocks in this revolution for modern cognitive neuroscience, and how the new domain of thinking about neural oscillations, to me, seems like the best candidate for pushing forward this quantum mechanic-infused science. And then finally, we'll wrap up today's episode talking about what would it look like to have a biologically plausible quantum computer, And how does this gel with sort of the more recent trends in cognitive neuroscience? So without further ado, I would impress upon you that the quantum revolution is already here. Google, IBM, a lot of these major companies are actively creating quantum computers at a scale that has never been, achieved in the past. And there's these historical landmark moments that are taking place in the recent couple years, such as quantum supremacy, in which a quantum computer was able to calculate or get the result of a computation that a digital computer could not reach even if it ran until the heat death of the universe. So it may not be non-computable, but the digital computer, the biggest one that we could create, would have to run for billions and maybe trillions of years. And this quantum computer solved this problem in a matter of probably seconds, maximum minutes. And so this is sort of this moment where quantum computers have really overtaken the information technology scene. And as digital computers have sort of plateaued in their effectiveness and in their evolution, quantum computers have emerged onto the scene just in time to take over the mantle of computation and to push the field of information technology forward. Furthermore, quantum biology appears to be here. And there was a discovery back in 2007 out of UC Berkeley, which made the argument that photosynthesis is necessarily using quantum mechanical principles. And while this original finding has been challenged to some degree recently, there's a number of other phenomenon in biology which appear to be at least leveraging aspects of quantum mechanics. And while we currently believe that chemistry and these really low-level biological processes are necessarily quantum mechanical, there's sort of this slow bleed through of quantum processes into higher and higher levels of biology, and for good reason, because we have not been able to understand a lot of these biological processes, and there's a bunch of novel mechanisms and tools coming out of quantum mechanics that might empower us to better understand biology and then reverse engineer biological processes. I always like to say that a blade of grass that can conduct photosynthesis is more advanced than our greatest solar panels. And so we're slowly catching up to the abilities that biology is able to enact. And so clearly there's a revolution taking place in lower order, small scale biology. And at what point does that get pushed into higher and higher levels of biology? And so we know that quantum physics is fundamental. And physics underlying, these Newtonian classical ideas of motion and cause and effect that we were building for the last hundreds of years, we now know that quantum mechanics underlies a lot of these processes. However, when we look at the brain, it appears that the brain is much too large, warm, wet, noisy. It is a macroscopic object. And so all of these quantum mechanical processes happening at a fundamental level appear to not be making an impact on the brain at first pass. However, if we look at the brain, we can decompose it into a series of brain nuclei. And those brain nuclei are composed of individual neurons. And those neurons are composed of proteins. And these proteins are composed of amino acids and interacting with molecules. And molecules are composed of individual atoms operating with subatomic forces. And we know for a fact that at this fundamental level, we have really bizarre behavior of individual electrons, individual protons, where there's examples like the double-slit experiment, where you have instances of wave-particle duality, where a photon will evolve into this wave-like superposition of multiple possible physical states simultaneously. And then if you measure, observe, interact with that photon, it gets reduced or collapsed into a very particular physical state. And so at this fundamental level, it appears like electrons, photons, protons are all undergoing these rhythmic processes of evolving into a superposition, being collapsed into a single point by some sort of interaction with the environment, and then evolving back out again. And so this constant evolution and measurement of these individual particles is underlying all of these higher order systems. And so the question is, where is the line? We now know that molecules exhibit a lot of these electronic resonances, these delocalized electron clouds, and they seem to exhibit a lot of these properties that can only be described by quantum mechanics. And then we look at proteins. And do proteins have these quantum mechanical forces also at play? Seems to be an open question, but there's a lot of mysteries in proteins, such as protein folding. How do millions of atoms within a protein organize their collective movement together? Could there be a delocalized quantum mechanical process that enables proteins to behave at this more macroscopic scale? There's people actively investigating this. This seems to be an open question. Neurons. Clearly, neurons could not be quantum mechanical. And even if a protein is able to sustain a quantum mechanical process, surely it would decay and disappear at the neuron level. However, couldn't you just link up neurons together? There's some theories about microtubules. There's some theories about the phospholipid bilayer membrane within a neuron, and how this membrane might allow for some quantum mechanical processes. And then we go up to the level of nuclei and onto the entire brain, and we have to draw a line at some point, right? If we want to say that only classical physics is prominent at the level of the entire brain, where do we cut it off? Where do we say, okay, we know quantum mechanics is at the lower level. We know it's not at the highest level. Is there a point where we have to cut it and say that it doesn't occur past this point, but under this point it is acceptable and allowed? And so I would make the argument to you that just because we have not discovered what that point is, doesn't necessarily mean that point has to exist, or that just because we don't know how quantum coherence and quantum mechanical processes would exist at these higher order macroscopic scales of biology doesn't mean that it fundamentally cannot exist. And it seems like every year there's new experiments coming out demonstrating room temperature quantum transfer is possible, demonstrating a larger and larger system is able to sustain quantum coherence, right? A quantum coherent process lasted for milliseconds when we thought it could only last for nanoseconds. So there's a number of findings, and if you go out there and search for them, you'll find so many of these instances where what we thought was a limitation is being chipped away, and okay, well, maybe there's a situation where it could be extended. Maybe there's another situation it could be extended here or there. And so no one is saying that quantum mechanics just shows up at the level of the brain for free, but instead the argument is that through biology, evolution has sort of created these mechanisms and these tools for sustaining and creating larger and larger scale quantum mechanical processes. And so just because we haven't reverse engineered or fully understood what those are, doesn't mean that they're not happening. And so let's look into the brain and see which phenomena seem to defy our classical understanding. So I'm going to sort of dive into the mystery of consciousness. So what is it about consciousness that is so mysterious and makes it so challenging to ground into biology? And what are the solutions that quantum mechanics might provide? Why is there this need, this desire to have a theory of quantum consciousness? So the first mystery I want to talk about is the sense of self. And this is the idea that you feel like you are a you, that you have a holistic self, a single entity which you identify with and say, this is me. And is this just an illusion? So if we go into the physicalist, reductionist, quantum mechanics doesn't matter paradigm, then we have to say that the brain and the body has generated this illusion of a self. right? And so there's like a little person inside of your head, which is not real, but is actively being created by the brain as sort of a theatrical show. And Daniel Dennett calls this the Cartesian theater. Why would the brain go about creating this theatrical presentation to an imagined illusory self when you could just do stuff? You could just interact and react with the world around you. Why bother to create an internal entity? And it seems really challenging to create a single entity out of a physical brain, which has all these tiny little components everywhere. At what point would a single entity even emerge? And that would seem like such an effortful thing to have to create through the physicalist paradigm. So what does quantum mechanics provide as a solution? Quantum coherence. In quantum mechanics and in quantum computation, there is a push, there is a drive to create a single large quantum computer. And so while in digital computation and in sort of classical frameworks, you just want to create a bunch of dedicated little processors everywhere, in quantum mechanics, the computational power of a quantum computer scales with the size of the quantum computer. So you want to get a really large quantum computer that has many, many quantum bits inside of it. And all these quantum bits are entangled, working together. And the challenge here is creating and sustaining quantum coherence. And quantum coherence is basically an energy barrier from the environment where you need to sustain these more subtle properties of quantum mechanics, and you want to create this single large-scale quantum computer. And so, hey, we think that we're a self. We think that we are one person. And in quantum computation, you want to create a single computer. You want to create a giant single entity that exists simultaneously. And so in quantum mechanics, there is a very big push and drive to create a self. If biology is working with quantum computation, it would be computationally efficacious to create a single large-scale entity within biology. So the human mind is not just along for the ride. It's not just a fun little thing that was created by chance, but it is a computational force essential to the processes of the organism. The second mystery, free will. And this is a very nebulous topic. It's very hard to define, but we have the sense that we have agency, that we make decisions, that we have a moral responsibility for our actions and what we do. And yet, however, it is very challenging within a digital, classical, physicalist paradigm to make any explanation of free will or why you would have an agent performing some action. And so if I am sending words through the air at you and you're listening to my words, am I causing the future of your reality? Are my words impacting you and causally manipulating or altering your future based on the words that I'm saying? And from a purely physicalist paradigm, you would just say, no, there's a bunch of neurons. The neurons are responding to the environment. And basically, my neurons are interacting with your neurons in some indirect fashion. But the neurons just drive the proteins, which drive this or that, which drives a muscle, which makes a sound wave, which hits your ear, and that causes some cascade of physical effects, and then it goes up to higher levels of your brain. But there is no me, there is no you, there is no causal free will impact of me onto you. However, in quantum mechanics, there's this really fascinating process called the collapse of the wave function. And really, this is sort of evidence that quantum mechanics is incomplete or not fully described. And even though I'm talking about quantum mechanics as this like beacon of new ideas and this new fully fleshed out theory, quantum mechanics is fundamentally mysterious and isn't really a resolved theory in and of itself. There's a lot of debate within the physics community of how to resolve a few mysteries. And one of those mysteries in particular is the collapse of the wave function, we have a system that evolves out into all these different physical states that could happen, and then somehow it gets reduced, and we can derive the probability of each of these different events occurring. But there needs to be this measurement event, this collapse event, which comes in, changes the system, and reduces it into one state or another. And it's fundamentally unknown what is driving the collapse of the wave function. And so one theory is that consciousness is somehow related to this collapse of the wave function. And if we suspend our disbelief and accept that there is a quantum computer that is your mind, that exists in your brain in some distributed non-local way, then the collapse of the wave function is you enacting your agency upon your own brain. And this is some way that free will is genuinely occurring, and that your mind, your thoughts, your will actually has an agency over your brain. And so while quantum mechanics doesn't necessarily understand or give an explanation that's fully fleshed out for free will, there is room within the unfinished theory to have consciousness, to have some sort of causal agency. All right, the third mystery, which is a little more abstract, is this idea of meaning. And this is something I really love, and I'll try to impart to you why I think this is important. But the idea is that in a physical, reductive, classical framing of the universe, meaning is arbitrarily constructed through various associations. So there's just a bunch of random pairings of things together, and these random pairings of instances gives rise to some sort of meaning that is just artificially constructed. And here I like to say that it's like culturally determined. It's just infinitely particular and infinitely based on sort of the chaotic happenstance of the association. And maybe throughout your life you build some meaning and you find it meaningful, but it's really just some arbitrary collection of associations. And what's missing here is this idea of truth, of some universal meaning, something that kind of extends beyond the individual. And so what could this be? And is there anything in quantum mechanics that hints at this? And this is definitely on the speculative side, but in quantum mechanics, there's something called entanglement. And entanglement is that when you have two systems that are interacting, if you then separate them in space, you can have this sort of spaceless, timeless relationship between these two elements because they were at one time connected. And so this entanglement is sort of the stronger version of these non-local, non-physical connections. But there's also been posited what's called hidden variables by, for example, David Bohm, where there might be a web, a network of hidden connections between all these different quantum systems, and it's not outside, well, it's outside of the current theory, but it's not outside of the realm of like scientific inquiry, where maybe there is a way through entanglement, through the spacelessness, the timelessness, of creating some sort of universal domain which is able to tap into some bigger sense of meaning that's transpersonal, that goes beyond any individual. And David Bohm called this the pilot wave, like the wave of the entire universe. John von Neumann, he called this, I believe, process 3, which was a process that sort of encompassed the will of nature herself. And so there's a lot of speculation that through entanglement and through these sort of hidden macroscopic connections, you could build something bigger than the individual, and you're plugged into this larger, grander landscape, and this could be a source of profound meaning beyond just the arbitrary constructed local reality. All right, so what is the state of modern cognitive neuroscience? So the state of modern cognitive neuroscience, I would argue, is very descriptive in nature. So for example, we have these massive labeling processes. We have the Human Connectome Project, which is essentially collecting as much data, electrophysiology, anatomical, on as many people as possible, gathering all this data, all these different cognitive tasks, different associations, make the mind think this, make the mind think that. And there's this big challenge of building a model of how the brain works. However, I think the primary problem here is that all of these approaches are descriptive and they're not generative. So it's very rare / unheard of that you would say that this model or this, neuroscientific finding is how the brain works, right? You couldn't make this from scratch in a petri dish, right? And so I think one of the challenges here is creating a generative model, is creating first principles which can generate and produce all of the complexity of what's happening. And I think that when we try to shove this into the classical physicalist paradigm of digital computers, we run into these roadblocks and we run into these sort of just like shortcomings of, okay, I mapped out every neuron in the brain. Okay, I have all the connections. Okay, now what, right? There is nothing that leaps out of that which suddenly has the meaning of consciousness inside of it, right? We're just sort of like stamp collecting, gathering together all of these, meaningful anatomical connections, meaningful cognitive associations between different circuits in the brain. But what is the end goal here? Where does this actually lead us, right? And there's a crisis within neuroscience and within psychology, and this has been called the replication crisis, where I think we're just struggling to figure out these first principles. And so this has taken the form of people being very skeptical of fMRI findings, like, oh, I heard all MRI findings are false. Oh, like all of psychology research isn't true. Like most of these studies aren't even true. And I think on one hand, this crisis is totally overblown because there is a lot of really good neuroscience and good psychology going on out there. And yes, it takes a while to build sort of a holistic understanding of what the field's knowledge is. But I think this crisis is really what's underlying it is that we don't understand first principles. What is the mind? How does the brain actually build information into the future? And so I think this fundamental unknown makes it really unsatisfying to have these descriptive studies. Someone was in love and then this circuit in the brain activated. Is that circuit love? Clearly not, right? It's going to take way more to generate the actual feeling of love than just looking at some neuron or some connection, right? Maybe you could say there's a bunch of arbitrary associations, but it doesn't feel compelling, at least to me. And I think fundamentally to all people, it's fundamentally missing some secret sauce, some fundamental truth is lacking in our current theories. All right, so there's a neural oscillations revolution occurring in cognitive neuroscience, and I'm going to briefly cover what are neural oscillations. And this is not necessarily a solution beyond descriptive, like all of this is fairly descriptive, but I think it gets us closer to the mechanism of the brain, and it gets us closer to thinking about what a quantum mechanical system in the brain would look like. So what are neural oscillations? Well, for a long time, we felt like there was this train of the brain chugging along, and the neurons were really like the powerhouse of the brain. The neurons are doing all the work. And then there's these electrical waves, these electrical oscillations that emanate out of the brain, but really it's just steam off the train engine. They're just along for the ride. However, in recent years, we've realized and discovered that electrical fields in the brain impact the firing probability of neurons. And so oscillations are impacting neurons. Neurons for sure are generating electrical oscillations and electric fields in the brain. But then these electric fields take on a life of their own and they impact and influence neural activity. And there's sort of this circular causation between neural oscillations and spiking activity in the brain. And so I'm going to talk about 3 mechanisms or ideas that have emerged from neural oscillations. One of them is synchrony, and that these electrical oscillations are a way where large swaths of the brain, large areas of the brain, can be synchronized in their electrical activity. And this can give rise to a bunch of coordination across many, many neurons. And it sort of is a way that this more macroscopic scale can take on a life of its own and process information, perhaps in a genuine way. So perhaps beyond just the level of individual neurons, you have entire regions which are generating these electric fields and interacting with each other and sort of creating higher and higher scales of activity. Similar to how proteins underlie neurons, now we know that there's brain nuclei and neurons are underlying those brain nuclei, but the nuclei and regions of the brain have their own sort of causal force, their own biological relevant signal that's generated at this higher scale. And there's different ways that we can uncover this. And if we sort of relate a bunch of perceptual processes and behavioral patterns, it seems like human perception and human behavior has a really clear mapping onto these large-scale electrical oscillations, perhaps more so than any individual neuron would relate to perception. And one example is that there's this 10 hertz, 10 times per second electrical oscillation in the visual cortex, often called the alpha oscillation. And this gives rise to this flickering sensitivity to visual information, where it seems like there's windows of perception that are being opened and closed. And if 2 flashes of light end up in 2 different windows of perception, you see both of the flashes. But if 2 flashes end up in 1 window, then you just really only see 1 flash. And we can predict a lot of perceptual phenomena in human awareness from these electrical fluctuations in various parts of the brain. Next up is coherence. It seems like multiple brain regions can establish coherence with each other by aligning their electrical oscillations. So if 2 regions are synchronized, where they're sort of vibrating electrically in sync, then information is preferentially shared between those regions. And if another region is not in sync, then that region doesn't receive that information. And then the final idea from neural oscillations is cross-frequency coupling. And I know this is a bunch of different mechanisms, but this third and final one is basically a way where you can have big, slow electrical oscillations, which are coupled to faster frequency oscillations. And through this coupling, you could have the faster frequency being guided by these lower frequencies. And this shows up in a number of cognitive control tasks where essentially the prefrontal cortex, a bunch of higher order information, needs to guide the motor cortex or the visual cortex, regions of the brain that are doing more like dedicated localized processing. They need to be guided by these more macroscopic oscillations. So what is going on here, right? So I set up some of the basics of quantum mechanics. I set up some of the basics of neural oscillations in the current state of cognitive neuroscience. And now we're going to sort of wrap up this discussion by wondering, is there a connection between these two? And so the question is, can we apply quantum mechanics? And so I think one clue to quantum computers is that they are inherently rhythmic. And so when you have the bit in a digital computer, you can imagine a quantum bit as basically representing the same 0 and 1, but having this sort of oscillation, this movement between these 2 different states of 0 and 1. And when we look at how a quantum computer functions, it is leveraging these oscillatory bits, these quantum bits, by sort of digitizing them, setting them up in a certain state, and then allowing all these rhythmic oscillating qubits to interact with each other, to gel together, to evolve together. And then you measure them, you get some output, and then the system repeats. And so quantum computers have this sort of rhythmic cycling to them, where they get new input and their output is measured, then they evolve in a quantum mechanical sense, then they get measured again and the system repeats. So when we're thinking about quantum bits being oscillatory and this sort of rhythmic nature to quantum computers, measuring a bunch of rhythmic processes in the brain, and while the discovery of neural oscillations is descriptive, could it be that there's these rhythmic computational processes underlying the brain, and that's why you would see a lot of this rhythmic activity in the electric fields of the brain? Next up, what do we also get from quantum mechanics? Well, we really need a central processing hub. And so let's take the example of a poisonous chemical enters into a cell, and the cell needs to send out some warning signals. And so what you'll have is a protein cascade where a bunch of proteins sort of interact with each other locally, and there's this chaotic, slow diffusion process where this information is transmitted. However, in the quantum mechanical framing, you could have a distributed quantum coherent system which is able to much more rapidly share this information and act as a unified processing hub that's able to generate a single response to this noxious stimuli and to guide behavior at this macro scale, right? And so if you're trying to get your inputs and your outputs through a chaotic process, how would you have a cell that's coordinating all of this activity dynamically? If you had a central hub, then it would operate much more effectively. And so the connection back to oscillations here, once again, is that oscillations represent these distributed electric fields that encompass entire parts of cortex. And so just from a sort of like systems design perspective, if we wanted to have a central processing hub in visual cortex, in prefrontal cortex, if we had a bunch of these chaotic little microsystems interacting, it would be very slow, it would be very chaotic. And to have these large scale modes or these processing motifs that are going to emerge or these macro responses, this would be enabled by having a macro system, and these large scale electric fields either are the substrate of this macro quantum system or some sort of signal that we're measuring as an outcome of this. But finding distributed large-scale electric fields in the brain is a good sign that there are these macro processing hubs. Next up, quantum computation is generative. So some of the problems with digital computation is that it's fragile. It needs to be programmed. There's an error in the code. There's a catastrophic failure. If you have ever programmed something, you know that one typo makes the entire program fail. And so in digital computation, it's inherently, fundamentally fragile. And if you were trying to think of like a digital computation emerging from the void, it seems so much more challenging to think about how a process would emerge. However, quantum computation is naturally occurring, and you have things like quantum search algorithms, which are very easy and potentially plausible to implement in biology without explicitly programming the search, right? There's something called like a quantum random walk, where if you just let a quantum system randomly move around, it's going to find more optimal solutions than if you just had a digital random walk, for example. And there's other things like the fact that quantum computers might be able to search exponentially large spaces in reasonable runtimes. So the fact that digital computers get stuck where they start running forever and they never find a solution, quantum computers can search very large spaces in much faster time frames, and they can get measured, they can get artificially reduced to, hey, generate an output right now. Doesn't matter if it's suboptimal, we just need the best answer that you can get. And so quantum computers have this measurement process which can get them out of the computational phase, and it has a lot of naturally occurring ways to search different energy landscapes. So there's just so much about quantum mechanics and about quantum computers which feels like you could create something from scratch which has a lot of computational power And all you would need is like a little barrier from the environment. And then, hey, it might just, start evolving in quantum random walking and find some optimal solutions to very hard problems without needing that external programmer sort of making things happen. And so when we compare this to neural oscillations, this is kind of a rough connection, but neural oscillations, is there some force underlying this system? It's rhythmic, so it's just searching these spaces, it's reaching whatever solution it's able to get in a certain amount of time, coming out of that computation, starting a new computation. And these neural oscillations either are somehow related to the substrate of this quantum computer or somehow a readout or maybe it is the steam off the quantum computer train. Who knows? Finally, I think there's a really cool avenue for applying quantum mechanics to psychology, totally avoiding any connection to how it would be implemented in the brain. And so these are quantum models of cognition. So I'm going to give an example here, which is there's basically a bunch of instances where humans appear to be making irrational decisions based on classical probability theory. However, if you look at it from a quantum probability theory lens, we appear to be actually making rational decisions. So here's the setup. Linda looks like a feminist. Bank tellers are rarely feminists. And so the question to you is, please rank the following situations and how likely they are. Option 1, Linda is a feminist. Option 2, Linda is a feminist and a bank teller. Option 3, Linda is a bank teller. Most people will say in that order that most likely Linda is a feminist and not a bank teller. Second most likely, Linda is a feminist and a bank teller. And third most likely, Linda is a bank teller. However, if we look at classical probability theory, we can think of the sphere of feminists, the sphere of bank tellers, and then the intersection between those two. And just by definition, even if feminist is the biggest one, bank teller is by definition larger than the intersection of bank teller and feminist, right? Sort of the overlap between the Venn diagram of bank teller and feminist is always going to be smaller than the bank teller. So you hear this and you go, oh, of course, I should have thought of that. Humans are dumb and we think irrationally. However, if you apply quantum probability theory, and I won't go into the details here, you can imagine there's a bank teller axis and a feminist axis, yes or no, for either of these questions. And what you can do is you can think about the setup of this question. In the setup, I told you that Linda was, she looked like she was a feminist, and that bank tellers are not typically feminists. So by telling you that Linda is a feminist, I am actually measuring your probability space of this scenario. You make this measurement, Linda's likely a feminist, and then after that measurement is conducted, now we look at the probability that she is a bank teller, and that is actually smaller than bank teller and feminist. And so this is sort of a weird thing to think about, but essentially the breakdown is that in quantum mechanics, context matters and order matters. So if you ask one question before another question, you irrevocably change the state of the system. And now the second question is asked to the system within a new system, right? That question shows up and you're in a different state and you receive a different question. And so what's really cool here is you can actually explain that in this quantum probability theory, asking feminist and getting no, and then getting yes to bank teller is less probability than getting yes to feminist and then getting yes to bank teller. And so this is kind of this weird scenario, but humans might not be irrational. They just might be rational within a different paradigm than what we're used to working with. And so the idea here is, I think there's a real possibility that we are going to discover quantum computational models of human cognition that outperform classical models. And then we find neural oscillations that are mapping onto these different parameters of these quantum computational models. And we have evidence that neural oscillations are involved in these quantum computational models of cognition, and that the quantum computational models of cognition are the best explanation for human cognition. And yet we still don't understand the implementation, right? So this is a possible future where I think there's this top-down approach where we start saying, what is the closest relationship between brain activity and human cognition? It's neural oscillations. What's the best computational model of human behavior and human thought? It's quantum computational models. And then there's a connection between these models and neural oscillations. And okay, I don't know how it's implemented in the brain, but this is just where the data is pointing me. So what is the implementation? Briefly, what is the challenge here? I think the challenge is creating quantum coherence, creating the situation where these subtle quantum mechanical processes are able to sustain themselves in the brain. Do I know the answer? No. There's a lot of interesting work coming out from like carbon nanotubes or these other man-made constructions which have these really bizarre, wacky properties. And so has biology evolved to create these decoherence-free zones via geometric patterns at a molecular scale? I think that is one avenue for understanding this. There's the Hameroff-Penrose model where there's these delocalized clouds of electrons which can be spread out across proteins and reach these more macroscopic scales. There's some weird models about optical quantum computation with biologically generated lasers where basically a bunch of photons have their wavelengths matched and they create these lasers, and that could be a form of computation. And then David Bohm has some speculations on how magnetic fields seem to be necessarily quantum mechanical in a lot of ways because they're so distributed. So maybe neural oscillations, electromagnetic fields are somehow more fundamentally linked to quantum computation, and we're just not quite there. And maybe these bioelectricity patterns that are created have different properties than just canonical electricity. Who knows? I don't know how this is going to shake out, but I think that we should keep moving forward. And I really appreciate this approach of taking quantum cognition models, taking neural oscillations, working with where the data is pointing us, and then seeing where we end up from there. All right, so what is next? We also know that there is this bizarre property where we see a lot of electromagnetic fractal-like scaling in the brain where more macroscopic scales are mapping onto more microscopic scales. And this leads to the question, are we a part of some sort of hierarchy of nested observers within the body where information created at one level propagates to a higher level and propagates to a higher level? And so I think that, while I've spent a lot of time talking about quantum computation as sort of the next stage of information processing, I think that there is very likely additional forms, paradigm shifts in information processing beyond the current status. And so I think one clue here is that there's all these weird fractal-like patterns across brain activity. And could there be some new form of fractal computation or the like, which goes even beyond these current models that we're working with? And that is, maybe 50 plus years from today. All right, so thank you so much for your attention. Please check out the podcast I've created. It's available on YouTube, Spotify, and Apple Podcast. And thank you so much to all my mentors and my funding that I've received throughout the years. And I'll talk to you again real soon.